In the previous video, we took a look at standing waves when they were transverse. Now we're going to take a look at standing waves when they're longitudinal waves, and specifically we'll focus on sound. So it turns out that all the same considerations apply. And again, what will matter is what the boundary conditions are. So if your resonant cavity is closed on both ends, that turns out to be the same difference as if they were fixed on both ends, if it were a transverse wave. So here we will be demanding a displacement node, which that means that the air at either end here isn't moving, which makes sense because these ends right here aren't moving, and so that's what we need to match up with. Incidentally, though, if you take a look at acoustics texts, they'll often say that these endpoints are antinodes, and that's because they're talking about pressure. So here, say where you would have an antinode in the middle, so a displacement antinode. So I'll sort of schematically draw it like this. This would be our first harmonic. This would be a displacement node here. This would be a displacement node here. This would be a displacement antinode here, which means that the air molecules would be vibrating back and forth the most violently. If we remember from Bernoulli's principle, Bernoulli's equation, that means that there's a kinetic energy density associated with those air molecules. And so accordingly, the pressure has to drop. So that means that the pressure here and here will be higher and lower here. So in acoustics books, since they're usually interested in dropping in some sort of pressure measuring device into the cavity, they will call this a pressure antinode, a pressure node, and a pressure antinode here. As a physicist, I'm looking at it from the point of view of the displacement of the air molecules. So this will be a displacement node here and a displacement node here. And then say if this was the first harmonic, we would have a displacement antinode here. Of course, that's right now we've got one loop. We could fit 2 loops, 3 loops, 4 loops, whatever. So it turns out that the harmonics are exactly the same as they are for the fixed case with a standing transverse wave. If both ends of your pipe are open, so for instance, we might be looking at certain kinds of organ pipes. Certain kinds of organ pipes can be well modeled as being open on both ends, or just plain a pipe. Here, since we're open at both ends, this is where the air is going to be most free to oscillate back and forth. So here we would have a displacement antinode. Whoops. There we go. So at the ends, we would want displacement antinodes. Here and here. And then say if this were the first harmonic, we would have a displacement node in the middle. And again, if you look in an acoustics or probably musicology text, they are likely to reverse the names node and antinode, but again, they would be referring to the pressure, not the displacement of the molecules. So if we have an open boundary, this is the same difference as free, the same results. if it's if it were a transverse wave. And then finally, there are other organ pipes that are closed at one end and open at the other. This is done especially for, as we'll see, for very long wavelengths, because since the pipe needs to, in these situations here, the pipe needs to be half the wavelength of the sound that you're making. When you get to very low notes with very long wavelengths, you start running into the practical issue that you run out of building to put the organ pipe into. So in that case, they switch to a closed open type of arrangement. And that's going to be the same difference as fixed free. So here, instead of us sticking in one loop for the fundamental, we would be sticking in a quarter of a loop. So this would be a displacement node here and a displacement antinode here. Now, of course, we can have higher harmonics. So in the case here for a closed open, you'd first have half a loop, and then the next harmonic would be if you had 1.5 loops, then 2.5 loops, and so forth. And that will be what I'll be demonstrating in the video clip that I'll be dropping in next. At one end of the device, you'll see that there's a speaker, and I can move a plunger. And I'm moving the plunger to where the note is sounding particularly loud, and that will correspond to where I have found a resonance. As I move the plunger is always going to demand that there be an antinode, a displacement node at the plunger. At the other end where the speaker is, that's almost but not quite an antinode, because literally there is some edge to the pipe at the end of the pipe. It's not like the perfect mathematical ideal of an open end, and so there's a tiny bit of closedness, and so technically the displacement antinode sits just a little bit outside the pipe. So you'll notice that when I mark the first harmonic with a clip, that distance will be a little less than half of the distance to the second resonance that I find, where I've moved the plunger an entire loop. And again, when I find the next resonance after that, I moved the plunger one more loop. You'll notice that first clip is sitting just a little bit short of what looks like half a loop compared to the others. And that's because very technically the antinode sits just a little bit outside the pipe and not perfectly at it, but it's not a huge difference.